So before we go for the next discrete circuit MOSFET amplifier, let's go back to our problem. This one, right? Previously, we have wrote the problem but solved only for the DC analysis, right? Now we can do the AC analysis at this stage, right? Because here we had MOSFET amplifier, the common source one, with a source resistance, right? So it means we have to use this model, right? So let's do it. So this would be the whole AC equivalent part, right? Only this will be grounded, right? This will be shorted, this will be shorted, right? So then you can replace your transistor with the T model, right? T model is gate, drain, source, a gate to source internal resistance, right? Not externally. And then drain would be behaving as a current source controlled by this VGS. Okay, now we can connect other things. At source we have a source resistance. At drain we have RD and RL. RD and RL grounded. R naught is not going to be considered for T model, right? And then for at the gate side you would be having a parallel combination of these two resistances, which is RG, right? Computed previously while performing the DC analysis, and a practical signal source having a output resistance as R signal, right? Output resistance of this V source. And this equivalent model based circuit of this amplifier is not completed until we compute the newly introduced parameters, which are GM, right, and 1 by GM. GM for this current source and 1 by GM for this T model resistance. So GM is ID over 2 VOV. When we put these values, we got this. 1 upon GM would be 1.2 kilo ohm. You can see it was only 1.2 nearly when we used common emitter amplifier with emitter resistance, right? But here the input resistance of MOSFET is higher than that, right? So it's a good selection. R naught is neglected because of using T model. Okay, so now we are at the stage to give the gain formulae. So as we did previously, write the relations of common things that you can, for example, Vi would be across Rin, and Rin is Rg only, right? Because there is no current going inside. So this resistance is not coming in parallel to not even 1 plus beta or something. And we don't have any 1 plus beta relation or beta relation, right? Because of no Ig. So V in will be equal to Rg divided by Rg plus R signal into V signal. Simple voltage divider by configuration between these two resistances, right? So this is V in, okay? And then this V in is actually from gate to ground, right? And according to this T model, it says that you have from gate to ground, then this VGS gate to source and then source to ground voltage would be the two parts of this VI, right? So it means VI is further divided in between these two resistances. So how about finding VGS out of VI is the voltage across this resistance out of these series resistances is simple voltage by divided by configuration 1 by GM divided by 1 by GM plus RS into VI will be equal to VGS, right? The same thing. Or we can write the VGS relation directly with the V signal if we put VI from here, right? It's up to you. And then we can write the equation of the output. Output is the voltage is current multiplied by the resistance. So the resistance are only these two. Parallel combination of these two would be having a current, which is this I, or we can say GM VGS, right? So current times these resistances will be the voltage across these at this terminal, right? But with minus sign because this is the current leaving terminal for these resistance. So V out is minus Gm VGS, the current value and the resistance value overall, right? So now we can put VGS equal to this if we want to have AV relation, right? Put it down, then you have this relation, or you can cancel out this. You have only 1 by Gm plus Rs into Rd parallel to RL is your AV. Remember, this is not AV, this is V out. If you bring it down, then this will become AV. Okay, or if I put VGS directly to this relation with VSG, or in this equation we put Vi equals to this one. In both cases we get this one, V out with the relation of V signal. Now if we drag this down, then this relation is equal to the GV. Okay, this is equal to GV because we already dragged down the V signal. So if we simplify these two things, change the position and put it on the top of this one because all are multiplying. So this is the relation in your book, written in your book. Even they used I, they found I here. So it's up to you. V I R. We bring V from here. If we bring I from here, it would be the same because we are using the same relations. Okay. So this is all about the AC analysis of our given problem. Okay, so now we can go to the remaining discrete circuit amplifiers, the common gate and common drain amplifiers. So common gate amplifier would be having a relation in which the AC, at least the AC signal will see a ground or common terminal at the gate, and the signal is applied at the source, right? Because if drain is available, it will prefer to be the output terminal, right? So then source will compromise as the emitter do in BJTs. How to find the gain relations? We can replace this with its AC equivalent model, the T model, right? Because we have input at the gate, at the source, right? And here they used I, and in our case, we used in common base amplifiers, we used RE. So here you can also think of RS here, right? So if you have RS, it will be here. If it does not have RS, it is the circuit which is given by this book. Okay, so if you suppose RS here, do the calculation about that as I did in common base amplifier. Okay, so now replace this transistor with its model, then gate is ground as far the AC equivalent circuit is concerned. This will behave as ground in AC signal. RL at the source, we have capacitor which will be short circuited for the AC signal and R signal, right? So now if we find the current from here, then that current multiplied by the resistance with minus sign will be given out. Okay, or if we find the value of this voltage, then this drain current will be equal to Gm VGS. Okay, so let's find Gm VGS, right, as we are doing from the starting. So what would be the VGS? Here you can see V signal is appearing, is you can see these resistances in series, right? This one and this one. So it means part of this will be appearing here and part of this will be appearing here. So part which is appearing here can be found as only voltage divider by 1 by Gm divided by 1 by Gm plus R signal into what? V signal, right? And this is equal to what? VGS or VSG? It is VSG. You can see from here to here and here to here. So what is the relation of VGS? It will be having a negative sign. So minus 1 by Gm at the numerator divided by, at denominator we have 1 by Gm plus R signal and whole multiplied by V signal. Okay, so we have minus sign already in VGS relation with the V signal. Okay, and how about the output equation? It will be equal to V out is equal to minus Gm VGS minus Y, because this terminal is the current leaving terminal for the parallel combination of these resistances, right? Multiplied by the current which is Gm VGS. So minus Gm VGS, V out is minus Gm VGS into RD parallel to RL. Okay, And then when we put VGS, which has minus sign itself, already told you, then we got the relation as positive as we found in common base amplifier. It means common gate amplifier also, like common base amplifier, did not invert the phase of the output as compared to the input. It means the output is in phase with the input signal, right? So please do it yourself. Again, here they show a current source also. So it will be having the same relation, because for AC equivalent circuit, this current source will be open circuited. You will finally have the equivalent circuit like this. Okay. So this is the common gate amplifier. This is the relation I told you we had found with positive sign, right? We had found already. So the common drain amplifier or source follower, right? Here it would be having no RD. The VD is directly volt coupled to the DC source, and when you want to find the AC equivalent circuit of this signal, then this drain is appearing as ground for the AC signal, similar to what the common collector was. Okay, because gate is available like base, so it will prefer to be the input port, then drain has to source has to compromise to be the output port. Okay, so if we have a current source here, then it will be open circuited. You will having only this circuit in the AC part. Otherwise, if you have RS, then RS will also be available here. So in any case, you have output at the source, so it means you can replace this with the T model. Here they did the AC analysis directly on the circuit, but we can do this one, and I will recommend you to do this. Okay, so replace the transistor with this one. Now you can consider the early effect also, right? T model has 1 by GM. At the gate you have RG, and source, at the source you have RL. At the source you have RL only. If you have RS, please put it here, then it will be the parallel combination of these two things. Okay, R0 is also coming in parallel, because this terminal is common for this, and this terminal is grounded, this terminal is grounded. You can bring it down as it is, as did for common collector, right? So now you can find the relation, the output of this value. How? Vin is the signal appearing across this R input, and Rn is nothing but Rg. So Vi is Rg divided by Rg plus R signal into whole multiplied by V signal, right? And this Vi will be appearing from gate to ground, right? So gate to ground, okay? And this Vi and is then further divided into this resistance and this resistance, right? Series combination of this. Do we have to find the VGS? Because we don't need VGS, we don't need this current to find the output. Output is here. So it means Vi from here to here, one part will be VGS, another part will be Vs to ground, which is V out. So just write the direct relation of V out, right? So V out will be the part of Vi which is appearing across RL and R0, and if we have RS, then RS also. So R0 parallel to RL divided by R0 parallel to RL plus 1 by GM multiply by Vi is your V out, right? And Vi is, if you want to put the relation directly to the V signal, Vi will be equal to these two resistances, voltage divider relation and V signal, and when we bring V signal down, we get VGB. Okay, please, please do listen this part again and write down as I dictate, and you will come to this relation. Please consider with the common collector, right? It would be the similar case, okay? But even simplest than that, because no IG, no beta 1 plus beta or something. What is appearing here is same is here, okay? So this is all about discrete circuit MOSFET based, enhancement type MOSFET based amplifiers, okay? So here comes your homework number 8. Luckily again, you don't need to submit it, but please do it yourself. If you have any problem, concern with me. Similar type of problems can be expected in terminal examination. MCQs would be there, maybe some fill in the blanks, but that fill in the blanks need to be having some rough work. I recommend to do fair work for that as well. Maybe you need it for the upcoming questions. Question will be randomized for the whole all the students. Maybe values will be changed. So please don't try to cheat yourself.
Thank you very much.